All right. Good morning and hello, everybody. Hope everybody's doing well. Let's go ahead and jump into our next lesson for calculus. So let's recap. We're in Unit 8 right now, right? So we have we're learning about different types of equations in calculus, right? So we've kind of touched on a few rectangular equation stuff, which is stuff we've been working with y equals x type of equations. We've learned just some additional formulas with that, arc length, surface of a surface area, stuff like that. And then we spent one day talking about parametric equations, kind of just doing a little bit of pre-cal review on that, touching on what a parametric equation is, what the form looks like. We did a few types of math problems that you see in pre-cal with that. But today is all about doing the calculus behind parametric equations. So all the stuff we've learned in the past that we can now do with parametric equations, derivatives and integrals and uh, arc length and all that stuff. Okay, so today's a little bit longer of a lesson, so I'm going to try to get through as much as I can in this video. And then whatever I don't finish, we'll just finish together. Okay, so we're going to start off with the basics. We're going to just kind of go in order here. The derivative of a parametric equation. Okay, so remember, a parametric equation is x equals some equation and y equals some other equation. We'll call it f, I should say f of t here, I'm sorry. We'll call it f of t and g of t. Okay. Well, whenever we talk about a derivative, the derivative is in the form dy over dx. That is the derivative of y with respect to x. So if I want to figure out dy over dx in terms of a parametric equation, it is the derivative of y on top. It's dy on top, which is the derivative of my y equation. Okay, so I'm going to call that dy over dt. And that's divided by dx, the derivative of my x equation. So I'm going to call that dx over dt. And if you want to use the same notation that I'm using above here, you can call that g prime of t over f prime of t, right? I mean, it's actually not that terrible. It's all it is taking the derivative of y divided by the derivative of x, and that's how you take the derivative. Makes sense. The derivative is the change in y over the change in x, so it makes sense to take the derivative of y divided by the derivative of x. So let's look at an example with that. Let's move forward here. It says, let c of t equal t squared plus 1 and t cubed minus 4t. So this is like a form of parametrics, right? This is telling you your x equation and your y equation right here. It says find the equation of the tangent line at t equals 3, and then where the tangent line is horizontal. Okay, well, we have seen this question so many times before in the past. Tangent line. We know what that means. This is in the form y minus y1 equals m times x minus x1. Okay. So if I'm asked to find a tangent line, all you need is a point, okay, and a slope, and that's it. Right? So thankfully, with our parametric equation, is we can find our x and our y points pretty easily, right? We have an x equals equation and we have a y equals equation. That's the point of a parametric. And the t equals 3 is going to tell us my position for x and for y. So if I want to know it for x, it's just going to be, instead of t squared plus 1, 3 squared plus 1, which I'm getting to be 10. And for y, it's going to be t cubed minus 4t, or 3 cubed minus 4 times 3, which I believe is 15. Oh, bless me. Whew. Okay. So I got my point. My point is at 10, comma 15. I don't know why I wrote x. 10, comma 15. And now the new part is finding the derivative. The derivative is dy over dx, which is the derivative of the y equation divided by the derivative of the x equation. And that is an x, but my handwriting is awful. Okay? And the math behind that is super simple, right? You're just going to find the derivative of y first, which 3t minus 4t becomes 3t squared minus 4. And the derivative of the x equation would just be 2t. Okay? So if I want to know dy over dx, or the derivative at time equals 3, you just plug 3 into that, right? So it's going to be 3 times 3 squared minus 4 over 2 times 3, which I believe is 23 on top and 6 on bottom. So I got 23 over 6 for my slope. And now you have the 3 points you need for a tangent line. So now it's just y minus 15 equals 23 over 6, x minus 10. There you go. All right, what about the second part? The tangent line is horizontal. So find where that point is at. Find where that point is at. Okay, well, think about it. When is a tangent line horizontal? A tangent line is horizontal where the derivative equals 0, right? When the derivative equals 0, we have a horizontal tangent line. So let me do this in red. Okay. So I want to know when the derivative, which we already figured out what the derivative is. The derivative was 3t squared minus 4 over 2t. Okay. I want to know where this equals 0. Okay. Well, where it equals 0 is where the top part equals 0, right? So all I got to do is 3t squared minus 4 equals 0. And solving for t is not terrible. T is going to equal plus or minus the square root of 4/3. Okay, there you go. So whenever my parameter is equal to plus or minus the square root of 4/3, I'm going to have a horizontal tangent line on my parametric equation. Now, if it wanted to know the specific point, the x and y value, it's simple. You have an x equals equation and a y equals equation that you can plug this into and get the answer. Okay. But for now, we're just going to focus on just finding what the t value is. I think we're all capable of plugging that back into x and y equals and solving for the actual coordinate points. Okay. All right, good first problem. Second problem here says, find the slope of the tangent line to the parametric curve between, below at the point negative square root of 3 over 2, comma 1. And you're given an x and y parametric equation, right? We're given a position for x and a position for y. My parameter is theta. Okay. So it says find the slope of the tangent line. So all I'm worried about is finding the slope at this specific point. Okay, well let's think about this. This specific point right here is x comma y, right? Well, if I want to figure out the derivative, let's start with finding the derivative first. Let's start with finding the slope of the derivative. Okay, that's going to be dy over dx equals, right? Well, dy is going to be the derivative of 2 sine theta, right? The y equation, and that's simply just going to be 2 cosine theta. And dx is going to be the derivative of the x equation, and the derivative of cosine of theta is negative sine of theta. Okay, so we're getting to finding the derivative. That's fine. But the issue is I'm given an xy coordinate point, right? And I would like to know the derivative at that point. Well, the derivative is in terms of theta. Okay, I'm given x and y. I need to figure out what theta is. Well, it's not too terrible, right? We're given x and y, and we have an x and y equation. So think about it. If I have x is negative square root of 3 over 2, okay, well then I got negative square root of 3 over 2 equals cosine of theta. And I have 1 equals 2 sine of theta, right? And can I not just solve for theta? I know it's two different equations, but it's the theta that they share in common where they have that coordinate point together, right? I mean, they got to have the same position. So it's where the theta is the same value. So for instance, where is cosine of theta equal to negative square root of 3 over 2? Well, think back to your unit circle. It's going to be negative in the second and third quadrant. So that is 5 pi over 6 and 7 pi over 6. Right? And where is sine of theta equal to 1/2? Well, that's going to be in the first and the second quadrant. So that's going to be theta equals pi over 6 and 5 pi over 6. Okay. Now, if I compare the two answers together, the one they have in common is actually 5 pi over 6. Okay. So it's at that parameter that they have the coordinate point, negative square root of 3 over 2, comma 1. So this point happens at theta equals 5 pi over 6. So if I want to know the slope at this point, it's asking me what the slope is at the point theta equals 5 pi over 6. Okay. So I'm going to plug in well, 5 pi over 6 everywhere I see a theta. So that's 2 cosine of 5 pi over 6 divided by negative sine of 5 pi over 6. That's ugly handwriting. I'm so sorry. But let's see here. What is that going to end up equaling? On top, I believe this 2 times, I think that's going to be the negative square root of 3 over 2 divided by, and then negative the sine of 5 pi over 6. I'm just thinking about the unit circle. 1, 2, 3, 3, 2, 1. I believe is going to be 1/2. Okay. The 2's can cancel. And I'm left with negative root 3 over negative 1/2, which reduces to 2 root 3. So the slope at that point is 2 root 3. Okay. Okay, let me change back to purple. I like purple. Let's keep going. So we now know the first derivative. Let's talk about the second derivative real quick. Okay, let's kind of, it's a little bit different, but I mean, this whole lesson is about just a bunch of formulas, and I just want you to add these to your list, okay? If I want to do second derivative, we know that means to take the derivative, that notation right here means take the derivative of my first derivative. We have said this notation many times in the past, the derivative of my first derivative. So it's kind of a weird thing to think about here, but it's like saying, okay, dy over dx is the same thing as dy over dt divided by dx over dt. And we're taking the derivative of that. Okay. Well, there's some weird like manipulation that you can do here. Like you can kind of flip some things around here, like flip this around by order of operations. And you can rewrite this in the form dy over dx, take the derivative of with respect to t, over dx over dt. Okay. So let me just kind of put that in really, like, so that's the notation, but I think it helps to maybe describe that out a little bit. So the second derivative, let's kind of write down what that means. If you think about it, that first parentheses, this means right here, this top part means take the derivative of dy over dx. So it literally means second derivative on top. It means take the derivative of dy over dx, whatever you got. And then the bottom, dx over dt, means the derivative, derivative of, and we'll call it f of t because that's how we defined the x equals equation. So it's the derivative of f of t, or the x equation. Okay, so maybe add that to your list of equations, or the list of things that you need to know. Okay, I mean, it may sound confusing, but I promise you the example is super straightforward. All right, so let's do an example together. Let's start off in part A. X equals t cubed, y equals t squared minus 2t. Find the first derivative and then the second derivative. So we'll start off with part A. Okay, we'll just do this one part at a time. Let's not jump ahead. The first derivative is what we just learned, right? So that's simple. dy over dx equals the derivative of y, which is 2t minus 2, divided by the derivative of x, which is 3t squared. So we know that. Okay. But now the second derivative, so we'll call that d2y over dx squared. All right, based off that formula that we talked about, it's going to be the derivative, so dy over dx, the derivative of that. So that means the first derivative, taking the derivative of that. And then we're going to divide by the derivative of the x equation. Okay, so let's do that. So if I'm given this as my first derivative, the derivative of that is a quotient rule. It's going to be low, which is 3t squared, d high, or 2 is the derivative of high, low d high, minus high, which is 2t minus 2, d low, or 6t. So that's low d high minus high d low, all over low, which would be 3t squared squared, or 9t to the fourth. So that's the second derivative of what I found, divided by dx over dt. And the derivative of 3t squared, or the x equation, would just be, oh, I'm sorry. We already found that the derivative of the x equation is 3t squared. I apologize. So this means the derivative of the x equation. Okay. So I know that seems weird to do. I know it's not just as simple as taking the derivative. Okay. So what you got to do is you pretty much got to take the derivative and then just divide by the derivative of the x equation, and that's it. Okay. So I'm cool with you leaving it right here. I think it's going to be beneficial for us for the part B and part C to simplify this down a little bit. So if I do simplify it down just a little bit, maybe we can do like some same change flip actions and combine some like terms on tops here. This is like 3t squared over 1. If I do same change flip, 9t to the fourth and 3t squared are going to multiply together. So I'll do it right here. You're going to end up getting on the denominator 27t to the sixth. And on the top, if you were to combine like terms, distribute, and multiply some things together, you're going to simplify down to 6t squared minus 12t squared plus 12t, which would end up equaling negative 6t squared plus 12t over 27t to the sixth. Which, if you want to reduce that even further, it looks like there's a factor of 3 that you can reduce by to negative 2t, actually a factor of negative 3 and t you can divide out. So that'll be negative 2t plus 4 over 9t to the fifth. So if you left it as the first box answer, that's fine, but I'm simplifying it down to the second box because we're going to need it in parts B and part C. Okay. Okay, so let's try part B. I'm going to copy this over. We're going to do a new slide. So part B says, find the horizontal and vertical tangent lines for the curve. Now we know from lessons in the past, that has to do with our first derivative, okay, equaling 0 or undefined. So our first derivative, if you remember from the last part A, is equal to 2t minus 2 over 3t squared, okay? So if I want to know where this is a horizontal tangent line, let's start off with that. A horizontal tangent is where the top part equals 0, right? So I'm going to do 2t minus 2 equals 0, or really t just equals 1, okay? So when t equals 1, we have a horizontal tangent line. So if I want to know the exact points of that horizontal tangent line, okay, if I want to know the exact points of that horizontal tangent line, you got an x equation and you got a y equation. Just plug it in. It's 1 cubed, comma, 1 squared minus 2 times 1. Or 1, comma, I believe that's negative 1. So there is a horizontal tangent point. Okay. If you want to know the vertical one, well, again, that's not too terrible. So a vertical tangent line is where the denominator equals 0, right? So where 3t squared equals 0, and that happens when t equals 0. Again, if I want to know the point, just plug it into your x and y equation, and you get 0, 0. Okay. Cool. All right, and then the last question is asking about concavity. So I'm going to, again, do another slide here. And it's saying, discuss the concavity of the curve. Okay, so the concavity, remember from lessons past, has to do with the second derivative. So we got d2y over dx squared equals 4 minus 2t over 9t to the fifth. So that's what we found, right? All right, so remember that a concavity is where the second derivative is positive as concave up, negative concave down. Okay, and we have a change in concavity at points of inflection where the second derivative is either 0 or undefined. So let's consider the points where we're 0 and undefined. So that would be t equals what? 2 and t equals 0. So let's do a number line here and look what's happening between these points for our second derivative. Okay. If you were to plug points into the second derivative, say like a negative number, okay? Say negative 1, for instance. It's going to be positive on top and negative on bottom. So it's going to be negative here. If I plug in positive 1, it's going to be positive on top and positive on bottom. And if I plug anything to the right of 2, it's going to be negative on top and positive on bottom, so negative. Okay. So when we're discussing concavity, we'll discuss it in terms of t, right? We are concave down, okay? We're concave down whenever t is between negative infinity and 0, as well as 2 to infinity. Okay. And it's concave up whenever t is between 0 and 2. Okay, so whenever I have those points, now you can figure out the intervals for x and y again by plugging in these t values in there, but it's better just to leave it in terms of t. That's usually how they're going to ask it. Okay. Well, this lesson is taking a lot longer than I was kind of anticipating here. But that's okay. So like the next example was going to be an example again with finding tangent lines, concave up, concave down, first, second derivative. So it's very similar to the other problem. So we might just do that in class together later. And again, another one where we're trying to find the equation line. Okay, so this was practicing first and second derivatives between the last two examples. again, a first and second derivative problem. But then we were going to get into finding area underneath the curve. And that's what I was wanting to pick up together with y'all, but we're just going to have to pick up there tomorrow and maybe try to come back to these examples that I skipped over, these three if we have time. But they're all very similar to the ones we just did together. Okay, so we're going to do area underneath the curve together. We're going to do arc length together, and we're going to do surface area together. So it's a lot of formulas, but if you know the formula, you're going to be fine. That's what you're going to kind of see. Okay. All right. Well, I'm going to shut up now. Y'all did a great job. It's 25 minutes. I'm not going to go past that. And hopefully we kind of looked over this, and we'll be able to pick up right here tomorrow. Okay. So good job, guys. Thanks for bearing with me. Have a good day.